Okay, looks like we're recording now. Share screen. Desktop 2, yeah. Okay. Now that's kind of confusing. Having two screens now. Okay, hi everyone. Welcome to IEEE's Intro to Cryptography workshop, as you can see in the bottom right corner over there. The check-in code is that over there, blue crypto, with a 3 instead of an E and a 0 instead of an O. There is food in the back of the room if you want it. Okay. Yeah, let's get started then. Shoot, it's not. There we are. This presentation was probably streamed with not ACM Live because reasons. There's just a problem with no one using ACM Live and it costing money to keep up. So now we're using Zoom. Yay. Okay, so to start off with, imagine it's World War II, right? Okay. The Germans have the secret code that they've been using. Shoot. The Enigma machine. They've been sending messages to each other, and while the Allies can intercept these messages, they can't decode them. They don't know what the Germans are saying to each other. So actually, why don't you, these are some Enigma machine simulators that you guys can play around with. Why don't you go to these links? Can I copy that? Gosh, this is so confusing. Where's my Zoom chat? Chris, can you access it? Can you give them the link?
Yeah, give me a sec.
Okay, but anyway, this is what the Enigma machine looked at. You would have the letters over here, and when you clicked on one would light up and you'd have to write it down. Now, there are multiple different rotor settings and starting positions, as well as this plug board, which you can use to swap two letters just before they come out, like that, for example. Now, you could type up your message like, hello there. And notice that even though, for example, we used two L's in the plain text, what does it look like on the other side? I actually can't see it on this setup. You do not get two L's coming out. So what happened was when you clicked on one of these letters, these dials would turn, creating a completely new rotor setup, or the next rotor setup. So every time you hit a key, you'd get a different one out. And that's part of what made this so hard to decrypt. There is actually another one here. Let's open it, where you can kind of see all of the connections at once. And if you input something like that, you could see how each letter gets put in and then out in a very complicated fashion. Basically, there's a lot of redundancy here to make sure that it's really, really difficult to decrypt. In fact, the Germans thought that this code was just unbreakable. But of course, it did get broken. Let's go back to the slides. Okay, so first let's understand why they thought it was so unbreakable. So since there are different rotor settings and switchboard settings, there are a bunch of different ways to encrypt the same thing. So let's count them. In the first slot, you can choose 5 of the rotors. In the second slot, you can choose 4. Let me go. Where is it? In the first slot, you can choose one of the 5 rotors. In the second one, there are 4 left to choose from, and in the third one, there are 3 left to choose from. So that is 60 combinations. Now, each rotor has 26 starting positions because there are 26 letters in the alphabet. And that gets you 17,576 more combinations. And now the plug board over here is where a lot of the combinations are. So there are 26 factorial ways to arrange the letters, but the plug board, at least in the original Enigma machine, can only make 10 pairs. So there are 6 letters left over. So you have to divide that by 6 factorial. Now the order of the 10 pairs doesn't matter. So divide by 10, another 10 factorial. And the order of the letters in each pair don't matter. So divide by 2 to the 10. And that is this many possibilities. What is that? I can't even read that. Hundreds, thousands, millions, billions, trillions. Yeah, like 150 trillion combinations. But now you have to multiply all of that together and you get that big number. I'm not going to bother to read it. So that many possible combinations on the Enigma machine, that many different ways to encode a single piece of text. And at the time, the Germans thought this was unbreakable. You know, there's no possible way they could figure this out, because each day they would have a new combination for their Enigma machine. The officers of the German army kept this piece of paper that would tell them what combination to set their Enigma machines to at the start of each day, and it would change every day. So going back to the Enigma machine, let me just clear that. You'll notice that if I type something like hi, it gets outputted as IO. Then when I go back to the original, when I go back to the original setting and I type in the ciphertext IO, I get hi out again. Okay, so that's how it's meant to be decrypted. If you have the key which is the rotor setting, you can decrypt the message that you're meant to decrypt. Okay, now let's get back to how it was broken. The one flaw in the Enigma machine was that a letter could never be encoded to, where's my mouse? Is that a letter could never be encoded to itself. So you could make a guess about a phrase that might be in a piece of text, like, for example, the phrase Hail Hydra, and line up your guess with the location in the message that you thought had that phrase. Now, what remains to be done is still too much for a human to do, which is why Alan Turing and his team created the bomb machine. What it could do was it could go through all the rotor combinations, and for each combination, it could make a guess about a switchboard setting. It would then determine what the rest of the switchboard settings were based on that initial guess. And if it came across a contradiction, it then knows that that switchboard setting is wrong, and it would move on to the next guess. And the bomb machine could crack the code in about 20 minutes. So the idea was the Allies intercepted some German encoded message at the start of the day, ran it through the bomb machine for 20 minutes, and now they would have the rotor combinations for the rest of the day, and they could go about their business. This is possible because of the key information you have, the guess that you can make about what words are actually in the message. Okay. Okay, so let's break this down and talk about encoding things in general. To encode something, you're going to need a key. You apply the key to the plain text or the message, and you get out the ciphertext. Now, to get the plain text back, you have to apply a key, which is not necessarily the same key, which I'll talk about later, to the ciphertext and get the plain text back out. And the key in our Enigma machine example was the rotor settings on the Enigma machine. And if you input a message with the certain rotor setting and got out the ciphertext, you could then get the plain text back out by putting the ciphertext through the Enigma machine with the same key. Okay. So now let's talk about, to start with, let's look at substitutions, which are probably the first idea that someone might have if they want to encode a message. The Enigma machine is also a type of substitution cipher. It's basically you just replace a letter with something else. Like, for example, Morse code. Not that Morse code is supposed to be a secret cipher, but it is an example of a substitution. Each letter gets replaced with some series of dots and dashes. You already know about Morse code probably, so I won't talk about it. By the way, are you guys on campus? Can you launch that poll? Okay, A for yes, B for no. Watch people put C and D, yeah. Okay, it looks like most of us are not on campus, is that right? Yeah, I'm not either. Yeah, it's looking like around 70% are not on campus. 20% are on campus, and some people who selected C and D. Let me share those results. Yeah, I can't make the poll live, so the only options are A, B, C, and D. I can't make a yes or no. But yeah, those are the poll results. The reason I'm asking, can I close this? The reason I'm asking is because there is a piece of artwork on UCSD. This tower, which is found in Ravel, flashes a message in Morse code at the top, which says, "What hath God wrought?" The first message ever sent with Morse code. And yeah, if you're on campus, you should check it out. But yeah, that's all I wanted to talk about that. Okay, now the next kind of cipher, a shift cipher or a Caesar cipher. Basically, each letter is shifted down a certain number of places in the alphabet. If you go to this website, there is right there a Caesar cipher. So basically, Caesar cipher, if you choose the value 7, A is going to go down 7 places to H, and so on. So something like this text over here becomes that. And you can play around with this number. If you make it 8, every letter gets shifted 8 places down, and so on. And note that if you do 26, you just get the same text back, which makes sense, right? Because you're shifting it all the way over back to the beginning. Chris, can you give them this website, crypty.com? They're going
Yep,
to
I
need it.
posted in chat.
Okay, cool. They're going to need it for the challenges later. Presenting. Okay, now ASCII stuff. I wanted to mention this because it shows up in CTFs pretty often. Basically, if you're familiar with the, I can't actually click on my visuals, otherwise I end up moving to the next slide. If you're familiar with the ASCII table, then you know that each letter has a value associated with it in ASCII. And you can express that in binary or hexadecimal or base 32 or base 64, whatever. Those are very common for computers because computers operate in binary. So any base that is a power of 2 is natural for them to display. So yeah, what hath God wrought is that in binary, that in hexadecimal, and so on. Crypty.com, by the way, also has these. Yeah, it has base 32, base 64. I think if you wanted to do hexadecimal or binary, you might have to find some other sites or something, because I couldn't find one here. Okay, now the next one is pretty interesting. A symbolic substitution. You replace letters with pretty much anything you can think of. You recognize this over here, Orabish. It is actually a writing system in Star Wars. So if you ever rewatch or watch for the first time the Star Wars movie again, keep an eye out for symbols like these. They actually appear everywhere there. In some of the prequels, you can see them on clone troopers' helmets. In The Force Awakens, you can see this text on Poe's vest. But yeah, that's pretty cool. And mystery novels tend to like this kind of cipher. If you've read one of the Sherlock Holmes short stories, Adventures of the Dancing Men, there is the criminals are using these symbols to encrypt their messages, to encode their messages, and part of the story is Sherlock Holmes deciphering it, basically. The next one, oh yeah, Vigenère cipher. This is a substitution cipher which does require a key. So how it works is it needs a key which is a word, and it's going to go through each letter in the plain text matched with each letter in the key. So L is matched with K. Then if you go over to this chart, L, K, you get out a V. And then for O, that's going to be matched with E. In the chart, yeah, whatever, that just comes out as S. Then R maps with Y and comes out as P. And then when you reach the end of the key, you start over. So E is matched with K again. Crypty.com also has a very good Vigenère cipher. Where is it? There it is. You can put the text in. You can change the key over here. And then you get out different texts. I don't know if you've taken CSC 15L yet, but one of the assignments you'll have to do is creating a Vigenère cipher program in Bash. And one thing I wanted to mention, the idea of coding, which is like using different words or phrases to hide the original meaning. So like saying things like the chicken has flown the coop or the eagle has landed, which wouldn't make sense to anyone who doesn't know what they mean. And yes, to a certain extent, texting lingo is like this because it doesn't make sense to people who don't know what the acronyms actually mean. And they definitely mean these. Okay, now I have some fun exercises for you. Okay, based on what I've taught you, can you decode these? How much time should I give them?
Using Crypty, I'd say you should be able to figure this out in like 5 minutes.
Okay. Yeah, I'll just give you 5 minutes. Have Crypty open. Can you paste these strings into the chat? Okay, so let me talk about the answers to this one. Let me close the poll. Now this first one over here, it's actually multiple of the encoding techniques that I've told you about layered on top of each other. So you started recording, okay. So to decode it, as you've probably already guessed, this is base 64. So let us go to base 64. Decode what's going on. That's weird. Oh no, it's actually base 32. There we are. Okay, then you're gonna get this, which also doesn't seem to make much sense, but it is still part of the cipher. This one is actually now a Caesar cipher. It is, let's find out. Where is it? Is it not? No, actually, yeah. Because it's still not revealed yet. It's actually a shift by 13. And then finally, I've never actually decoded these before. It's the first time I decoded them, but I wrote down the answers. Yep, there it is. Okay. You get this wonderful message from my sister. Yeah, so I layered multiple techniques on top of each other to kind of confuse and confound you. I told you these ones were harder. Evil. Oh, you think this one is evil? Okay, I'm gonna get back to number 6. How do you know which decoders to use? You keep guessing. It is kind of evil. I did tell you these would be harder. Now this one is also not something I told you about. It's actually a very weird visual cipher. In fact, it's so weird that I wrote it out. There it is. What I did was I started writing the words like this. First one at the top left, then down and to the right, down and to the right, up and to the right, up and to the right. That's a space over there. And then you keep going like this, zigzagging up and down. And then what I wrote down was this red from left to right with a slash put between the next line. So yeah, that one was really hard. That one was really hard. You had to know that you had to write. Am I screenshotting something? No, okay. you had to know that you had to write this from left to right, and then go to the next line at the slash. And then what you would get is next challenge is Enigma machine default. Yeah, I was too lazy to write out more than that. I was also too lazy to pick a different setting for the Enigma machine. But the next challenge is an Enigma machine challenge. I think it's called Rail. Okay. Chris just said he thinks this is called Rail Fence, which me possibly. I don't actually know. How did I write it out? Okay, so I'll explain it again. Yeah, I should have written the original phrase. Let me paste the original phrase in the chat. Next challenge, Enigma machine default, okay? And how I wrote that was this. I wrote them zigzag like this. Next space CHALLENG and so on. And then when I wrote it out, finally, I read this from left to right. N space LGNACEFT ET and so on. And so that's what that was over there. This next one, does that make sense to you? Rail fence cipher. Okay. No, that's not the one I want. This is the one I want. So the next one is an Enigma machine challenge. I don't think I'm going to type all of this out. Basically, you have it at the default settings, right? And then you start typing it in. Shoot, I don't have them on both screens. Yeah, that one was a really difficult one. That's why I said I didn't expect people to get these ones. And so if you start typing this out, MIOMX. I hope this is working. I would look pretty silly if this didn't work. Yes, okay. It's typing it out now, but I'm not going to type all of it. I'll paste the answer in the chat. That's what that ends up becoming. Yay, you're cursed now. Okay, any questions so far? We'll talk about number 6 right now. Are we good? Okay, number 6 was... Okay, good point. Only I'm cursed, no one else. Whoops. Okay, number 6 is actually a complete troll. This is a random string of numbers and letters. Are we good there? If only this were in person, so I could see her. Okay, that's amazing. It's already been an hour. Yes, I'm the imposter. It's already been an hour and I have to move on now. Okay, now I just wanted to touch on a couple more ways to encode things. I'm not going to go too much in depth into this one, but this is a block cipher. Basically, you encrypt an entire block of text at a time, like, for example, 128 bits at a time. What's going to happen is you're going to take the plain text and cross it with an initialization vector, an IV. And then you're going to run the result of that through the key. So you're going to encrypt that. And then what you get out is a ciphertext for the first block, the first 128 bits. Now for the next 128 bits, you actually use the result from the previous block as the initialization vector for this next one. and then you encrypt that with the key, and so on. Again, not going to go too much in depth. Next one, hashing functions. Hashing functions is hashing function is used to turn a string into a hash. That's very difficult to reverse, even if you do know the algorithm. And this is used to like store hashed passwords or something. So even if the hash gets leaked, the password is still in theory safe. And a good hash function is pretty much going to be one way. So you run the original text through the function, get something out, and you're not going to feasibly able to get the original text back out just given the hash. It's highly sensitive to small changes in the original password, so that it's not easy to predict what a hash is based on a small change in the original password. It's collision resistant, which means you're not going to get the same hash for two different plausible passwords. Non-predictable, again, tying into being highly sensitive to small changes. You can't predict what the new hash will be just by changing the original password unless you actually calculate it. And deterministic. So you keep using the same text and you keep getting the same hash out. An example of this, because this shows up quite a bit in CTF challenges, is an MD5 hash. I won't go into how this is generated, but basically you put in any text and what comes out is a 128-bit long hash or 32 hex characters, and it's going to look something like this. Technically, although you can't reverse something like this, you can crack hashes like this if you have a password list. So there are plenty of tools online that have a database of known passwords and their resulting hashes. And if you have a hash of your own, you can input it into that tool, and it'll say, okay, this is the password that I know of that matches this hash. You can also use more advanced tools like Hashcat, which I won't get into now, to be able to get a password out of a hash with maybe just a few hints or something, like if you know the password is a certain length long, or if there are digits in certain places. Next, I think this one over here should be easily decipherable. If you just Google like MD5 hash cracker, and you paste that in and you decrypt it. It's not in our database. I actually don't remember what I used for this hash. Maybe another one will work. Okay, whatever.
You can use Crack Station, Sean. It'll work.
Crack Station?
Yeah, there's a link in chat.
Oh, there is. Where is the chat? Actually, I'm going to move on. I don't remember what I used for that, but I'm sure it was something simple like password. Okay, so let's get back to this. So basically, if you have a bad password, a hashing function is not going to save you. Okay, so let's talk about why this is important here. So as you know, the World Wide Web exists, right? There's information going across the world. More information is traveling across the world than at any point in human history, basically. And all that information needs to be secure. Just imagine what chaos would happen if anyone could intercept random emails, communications from the government, bank account information. So it all needs to be secure. So let's talk about one of the most widely used ways to secure information across the web, and that's RSA encryption. Oh, yeah, that was just what I talked about. And let's do it through an example, okay? Bear with me here. This is Aaron, and this is Sharon. Okay, and these two want to communicate with each other without anyone else dropping in on their conversations, right? Like their parents or something. What is the chat saying? I don't know. Okay. So what I'm going to do here is I'm going to walk you through a very, is someone pinging me on Discord? I'm going to quit Discord. Die. Okay. I'm going to walk you through a very bare bones example that demonstrates the math behind how an asymmetric encryption technique like RSA works. But basically, the idea behind encryption across the web is that, unlike the previous ciphers that I've shown you, you need a key to encrypt a message, but a different key to decrypt it. And the benefit of that is you can share this public key, the one to encrypt, with anyone. And as long as you're keeping your private key safe, the information that people send to you can be secure. Okay. Okay, so first of all, to have a pair of keys such that only one of them encrypts and the other one decrypts, there needs to be some kind of function that is easy to compute for the purpose of key generation, but not so easy to invert so that the private key can't just be calculated. Yeah, I just said that. So what's used in these modern encryption techniques is multiplying two large prime numbers together. You might have already known that. For example, if I asked you what is the prime factorization of 701,111, could you answer that? Anybody want to chime in? Okay. I mean, you might be able to if you spend a little bit of time. A computer could do this almost instantly, but compared to the question, what is 907 times 773? That's a lot easier, right? You can pull out your calculator for that, punch it in, and you get the answer. So that is something that's easy to calculate in one direction, but not so easy in the other direction. Now, like I said, since computers can pretty much do this instantly, actual prime numbers in 2048-bit RSA encryption are over 600 digits long, so they're really big. Okay. One more thing you need to know about is the modulus operator, which is like the remainder of A divided by B. So A modulus B, or A mod B, is just the remainder of A and B. And as an example, 10 mod 3 is 1, because 10 divided by 3 is 9 remainder 1. So you take the remainder. And okay, so let's get to the key generation. Sharon wants to send a message to Aaron. So Aaron is going to need to generate some keys, one public key for Sharon to encrypt her message with, and one private key for him to decrypt it himself. Right?
And this is why I say give hackers a bad idea.
Okay, sorry, that's my sister. Okay, so you need two prime numbers, right? Let's call them P and Q. Those are selected with a primality test, an algorithm to select primes. I'm not going to talk about it just for simplicity. Like I said, this is going to be a very bare bones example with small numbers. So let's say P and Q are 5 and 11, two primes, right? Now you need to find N, the product of those two primes. And that's easy. It's 55. Yeah. Now the last thing that Aaron needs is to apply what's called Carmichael's totient function. And that is pretty simple. It is just the least common multiple of P minus 1 and Q minus 1. And you get the answer to that, which is lambda. The least common multiple is pretty easy to calculate, even for really large numbers. You can use something like Euclid's algorithm for that. Okay, so in our example, to recap, our primes are 5 and 11. Their product is 55, and lambda is 20. Okay. Okay, so now to generate the public key. The public key is made up of another prime number E and the value of N, which is 55 in our example. Now E is any prime number between 1 and lambda. In real scenarios, this is usually set to 65,537. I don't know the reasoning behind that. But for our example, let's use E equals 7, right? 7 is between 1 and 20, and it's a prime number. So now the ciphertext can be calculated related to the original message by this equation. C equals m to the E mod m. So Aaron is going to generate this public key and give the key to Sharon. And it's okay if anyone else intercepts this key or something, because this key can only be used to encrypt. It cannot decrypt the messages. Okay. So now the message. Sharon wants to say something to Aaron. Let's just say she says hi. She's not very verbose. I don't know. Now the word hi needs to be converted to a number, because remember, this is a mathematical expression. I'm not going to talk about how it's actually converted to a number in RSA encryption, but for our purposes, again, since we want to work with small numbers, let's just say that each letter becomes the number that is its position in the alphabet, okay? So H is the 8th letter in the alphabet, and I is the 9th letter in the alphabet. And the way we're gonna encode this is we're gonna do it one letter at a time. So the first letter, again, if we apply our expression over here, that's gonna equal 8 to the 7 mod 55. And the second letter is 9 to the 7 mod 55. You could calculate that yourself, but I'll save you the time. What you get is 2 and 4. Okay, so that is the ciphertext, 2 and 4. Sharon is going to use this method to encrypt her plain text, which is just the word hi. It's going to become ciphertext, and she's going to give the ciphertext to Aaron. Now Aaron needs to be able to decrypt this with his private key. The key requires a number D and the product N again. So D is the modular inverse of E and lambda. You don't really need to know how this is calculated, but the expression looks like that. And what you get is D equals 3. So now with that, he can use the decryption formula. The original message equals the ciphertext to the power of D mod M. And this key being, the value of D, he's going to keep secret. He's going to keep to himself. Okay, so going back to the message, Aaron receives the ciphertext 2-4. And now he's going to decrypt this one letter at a time. So you apply that same formula, you get that, and I'll save you the time. What you get out is 8 and 9, which is exactly what the plain text was earlier. Amazing, right? And now Aaron's happy because the girl has finally talked to him. Yay. Is the chat saying anything?
Nope, you're good to go.
Okay. Okay, so a few notes. This is obviously a super simplified version with very small numbers. And I glossed over a few things like how the primes are generated. Another thing is usually the messages themselves aren't encrypted, but rather the authentication that you need to view the message is encrypted, so that it's just more efficient. You don't have to encrypt the entire message with these massive prime numbers. Secondly, padding is used to embed extra data into the message to make it harder to break. So to get a sense of why you need to do this, think back to the Enigma machine example, right? Once you could make a guess as to what a certain phrase in the ciphertext could be, you could then start to decode it. Similar sort of thing with what we just talked about. If someone intercepts the message and they know that the message is just 2 letters long, well, how many 2-letter words are there in the English dictionary? Not a lot. And if you made that guess, then you might be able to determine what the private key is, work backwards from there. And that's why padding is used. And then finally, there are better forms of encryption, like elliptic curve cryptography. I'm not going to talk about it. Aaron did do a workshop on this last spring, but the way the numbers are generated in ECC, it's just more secure than RSA. So the same amount of security that you could have with 2048-bit keys in RSA, you could have that same amount of security with, say, 256-bit keys in ECC. Okay. Now about cracking RSA encryption. Technically, if you have enough time and computing power, you will be able to do it. What you need to do is factor that number, right? You need to figure out the 2 primes. Once you figure out the 2 primes, you can figure out the value of Carmichael's Tottian function, and from that you can calculate the private key. But in practice, with these extremely large numbers, our current computers cannot do that feasibly in a small enough amount of computing power and in a short enough amount of time. Another thing is, if the random prime generation isn't random enough, like if it's pseudo-random and you could predict what numbers are going to come out given the seeds, it can be easier to guess the primes. And the primes must be large and far apart. Otherwise, the factorization can be computed easier. But if implemented correctly, then RSA encryption should be safe. Again, it needs really large numbers. Okay, unless quantum computers. Interesting. So yeah, quantum computers can actually break RSA encryption without the need for all that time and computing power that classical computers need. So this is close to the end of the presentation. Without going too much into detail about how these work, basically a quantum, by the way, this is a pun, a bit about how they work. Ha, ha, ha. A classical computer stores bits as either a 0 or a 1, right? And if you read a bit and you get a 1, it means that that bit was stored as 1, and it was a 1 before you even looked at it. Whereas in a quantum computer, the qubit is in a superposition of 0 and 1. And its wave function collapses to one of the two outputs when you observe it. And this fundamentally changes how the computer can, do stuff. Again, not going to go into too much detail because we don't have time, and also I don't understand this in very much detail. So yeah, that's just the general overview. So now if you want to break RSA encryption with quantum computers, here's how you can do it. You're going to need to factorize that number, right, into its 2 prime numbers. Is there something in the chat? Okay, numbers. What do you mean by authentication? Okay. Okay, so for the question of how characters are turned into numbers, I don't know the details of that either. And I said I wasn't going to go into it. It was just for the purpose of this example that I just simply said, okay, the numbers will be the positions they are in the alphabet, but the math still works out the same. What do I mean by authentication? Okay, okay, so the authentication is just another method of encrypting the message. So if you have a different method of encrypting the message, most likely a symmetric key, then you encrypt the message with that key, which is usually more efficient than doing it with RSA. And then that key you encrypt with RSA. So now that key is hidden. So you need to have the private RSA key to unlock the key that you then need to decrypt the text. That's what I mean. I thought that might have been a little confusing, so I didn't talk about it. Is that authentication key harder to crack than RSA then? What do you mean? Yeah. Yeah, I didn't want to talk about that because I thought it might have been confusing bringing up another set of keys. Hold on. Okay. Where was I? Okay. So now you need to factorize the number n, right, into its 2 prime numbers. Here's how you're going to do that. I should just escape. I wanted to highlight some of this stuff. Not all of this requires a quantum computer. This is the only line which requires a quantum computer. I'll talk about it later. So here's the algorithm, basically. First, you generate a random integer a, which is between 0 and n. Then you check if a is already a factor of n. If it did, you've found one of the factors. But if not, what needs to happen, and this is where the quantum computer jumps in, you need to find the period of a and n. I'll get back to that, but what R the period is it's basically the smallest number such that a to the r mod n equals 1. I'll get back to that again. And then you have this check. If r is even and a to the r over 2 mod n is not congruent to -1, then you found the answers. P is going to be the greatest common divisor of a to the r over 2 plus 1 and n, and Q is going to be the greatest common divisor of a to the r over 2 minus 1 and n. Don't worry if you're having trouble keeping up. Honestly, there's a lot more here that I'm not talking about because I don't fully understand it. So then you found P and Q and you return them. And if both of these statements aren't true, you have to regenerate your number A and do that again. Okay. So yeah, I just wanted to talk about it because I think quantum computers are really interesting. How many people are still here? 16. But yeah, that is, oh yeah, I wanted to talk about this. So the reason that finding the period R needs a quantum computer, okay, no problem. So that the reason that requires a quantum computer, when these numbers get large, it is again nearly impossible for a classical computer to do. It's pretty much going to have to try, all the different combinations and whatnot. But for a quantum computer, remember how I told you that each qubit is in a superposition and its wave function collapses when you observe it. So you have the multiple qubits that are all entangled with each other, part of this calculation, and when you and they are in a superposition of all of the possible outcomes. And then when you make a measurement, that wave function collapses to the one result. I'd say it's almost as if the quantum computer is checking all of the possible outputs at once. But again, there's a lot going on in quantum computing that I don't understand. So I'm not an expert to be able to tell you what's going on. But I just thought it was interesting, which is why I put this at the end of my slides. But that is the end of my presentation. Are there any questions? Yay. Thanks for coming.